Acid-base equilibrium. Calculating pH changes in a buffer solution. In this tutorial, we will be going over how to calculate pH changes in a buffer solution, how do buffers neutralize strong acids and strong bases, the effect of adding a strong acid to a buffer system, and the effect of adding a strong acid to a different buffer system on pH. Calculating pH changes in a buffer solution. When an acid or a base is added to a buffer, the buffer resists a pH change, even though the pH will change slightly over the course of the neutralization. Calculating the small amount that the pH does change requires two steps. First, we need to determine how the addition of a strong electrolyte changes the amounts of the weak acid and the conjugate base. Then we have to determine the new pH based upon the new amounts of weak acid and conjugate base. Important to know, reactions between strong acids and weak bases proceed essentially to completion, and reactions between strong bases and weak acids also proceed essentially to completion. As long as the buffering capacity of the buffer is not exceeded, one can assume that the strong acid or base is completely consumed by the reaction with the buffer. Let's look at an example. A buffer is made by combining 0.02 molar HC2H3O2 and 0.02 molar NaC2H3O2. The total volume of the buffer solution is 500 milliliters. So we have two reactions, the weak acid reacting with water to produce hydronium ions and the weak base, but we also have the weak base reacting with water to form the weak acid and the hydroxide ions. So the stress in this situation is adding 0.01 molar of HCl, which we know is a strong acid. Which reaction would be used to counter the stress? The ionization of the strong acid is HCl ionizes to form hydrogen ions and chloride ions. We need a reaction that is going to neutralize the hydrogen ions. So if you chose reaction 2, that is correct. Let's see why that's the case. So we have our strong acid in reaction 2 in a neutralization reaction. So in the beginning, the concentration of our weak acid is 0.02. There is no hydrogen ions present, and our weak base is 0.02. When this neutralization reaction occurs, we add 0.01 molar of the strong acid. As a result, the hydrogen ions from the strong acid are neutralized by the hydroxide ions produced by the weak base. This reduces the amount of hydroxide ions in solution. More weak base reacts with water to form more hydroxide ions until all of the hydrogen ions are neutralized. As a result of products being formed, the amount of acetic acid increases. This can be seen in the after section of the table, where the amount of weak base is decreased and the amount of weak acid produced is increased. As a result, the solution becomes slightly more acidic than basic. Let's look at another example. A buffer is made by combining 0.02 molar HC2H3O2 and 0.02 molar NaC2H3O2. The total volume of the buffer solution is 500 milliliters. So again, we have our reaction 1 and our reaction 2. Those were the same as we saw in the previous example, but the stress in this situation is adding 0.01 molar of NaOH, which we know is a strong base. Which reaction would be used to counter the stress? So the strong base is going to dissociate from NaOH into sodium ions and hydroxide ions. So we need a reaction that is going to neutralize the hydroxide ions. In this case, we're going to be using reaction 1, where the hydronium ions produced from the weak acid are going to neutralize the hydroxide ions. In the beginning, we have 0.02 molar of our weak acid, no hydroxide ions are present, and we have 0.02 molar of our weak base. When neutralization occurs by the addition of 0.10 molar of the strong base, the hydroxide ions from the strong base will be neutralized by the hydronium ions produced from the ionization of the weak acid. This will continue until all of the hydroxide ions are neutralized. As a result, this reduces the amount of hydronium ions in solution. More weak acid is going to react with water to form more hydronium ions and the weak base. As a result of products being formed, the amount of the acetate ion, the weak base, will increase. This can be seen in the after section of the table, where the concentration of the weak base has increased by 0.01 and the concentration of the weak acid has decreased by 0.01. As a result, the solution becomes slightly more basic than acidic. The effect of adding a strong acid to a buffer system on pH. Determine the initial pH of a 500 milliliter buffer solution consisting of 0.125 molar HC2H3O2 and 0.115 molar NaC2H3O2. The Ka of acetic acid is 1.8 times 10 to the negative 5. When we look at this stimulus, we realize that instead of doing a race table, we can use the Henderson-Hasselbalch equation. So the first thing that we need to do is calculate a pKa value. We can do this by using the formula pKa is equal to the negative log of Ka. Substituting in our Ka value from the stimulus, we can calculate that the pKa value is 4.74. Once we have this pKa value, we can write the Henderson-Hasselbalch equation. Then, looking at the stimulus, we can substitute in for our variables, where pH is going to equal 4.74, that's our calculated pKa value, plus the log of the concentration of our weak base, which is 0.115, divided by the concentration of our weak acid, 0.125, which is also from the stimulus. When we complete the calculations, the initial pH is 4.70. Now we're going to determine a new pH of the buffer solution after the addition of 0.02 molar HCl. So in the beginning, we have a concentration of 0.125 molar of our weak acid. No hydrogen ions are present, and the concentration of our weak base is 0.115. The change occurs when we add the 0.02 molar of our strong acid. The strong acid will be neutralized by our weak base, and as a result of this neutralization, we will add 0.02 molar of weak acid. So as a result, the strong acid is neutralized. We have 0.145 molar of our weak acid by adding these two values together. And when we subtract these two values, our final molarity of our weak base is going to be 0.095. We can now take these concentrations to determine our new pH. So we'll use the Henderson-Hasselbalch equation. We'll plug in our values of pH is equal to 4.74. That was our pKa value from the previous example, plus the log of the concentration of our weak base, which we just calculated, divided by the concentration of our weak acid. When we do this calculation, we determine our new pH to be 4.56. The initial pH that we calculated in the previous example is 4.70. The new pH is 4.56. So the pH decreases as more weak acid is produced. Notice that the decrease is relatively small because a buffer was involved. Let's look at another example. Determine the initial pH of a 500 milliliter buffer solution consisting of 0.155 molar C2H5NH2 and 0.145 molar C2H5NH3Cl. the Kb of C2H5NH2 is 5.6 times 10 to the negative 4. So the first thing that we're going to do is calculate Ka. We'll rearrange this formula to solve for Ka, where Ka is equal to Kw divided by Kb. Then we'll plug in our values, where Kw is 1 times 10 to the negative 14, and the Kb given from the stimulus is 5.6 times 10 to the negative 4. We calculate the Ka value to be 1.79 times 10 to the negative 11, and then we can use that number to calculate pKa. So we'll plug in 1.79 times 10 to the negative 11 into this pKa formula, and we'll determine that the pKa value is 10.75. We'll use this pKa value of 10.75 in our Henderson-Hasselbalch equation. The next step is to substitute in for our variables using the information given from the stimulus. So pH is equal to 10.75, which we just calculated, plus the log of the concentration of our weak base of 0.095 and our weak acid 0.145. As a result, our pH is calculated to be 10.78. Now we're going to determine a new pH of the buffer solution after the addition of 0.02 molar HCl. So in the beginning, the concentration of our weak acid is 0.145. No hydrogen ions have been added. And the concentration of the weak base is 0.155. The change occurs once we add that 0.02 molar of the strong acid. So again, the strong acid is going to be neutralized completely by the weak base, but as a result of this neutralization, some weak acid will be produced. When this goes to completion, the strong acid that was added is neutralized, and the concentration for the weak acid is 0.165, and for the weak base is 0.135. We can use these answers to calculate a new pH. So we'll use the Henderson-Hasselbalch equation. We'll plug in our values from the stimulus. We'll plug in our pKa value, which we determined was 10.75, and our final concentrations after the acid has been neutralized. When we do this calculation, our new pH is 10.66. So the initial pH is 10.78. The new pH is 10.66. So the new pH decreases slightly as more weak acid is produced. So what did you learn? We learned how to calculate pH changes in a buffer solution. We talked about how do buffers neutralize strong acids and strong bases, the effect of adding a strong acid to a buffer system on pH, and the effect of adding a strong acid to a different buffer system on pH. Need more help? Feel free to contact me. Have a great day.